Swayam Prabha. Digital India. Educated India.
When a question is asked, it is expected that you will answer. Simple answer is I don't want to compute energy. Are you computing energy when you are solving time independent Schrodinger equation? How many of you solved particle in a 1D box? Can you please raise your hands? Particle in a 1D box. You did not solve except 2 people? Solved. Then why are you not raising the hands? You have hands, you can raise. I asked you to raise. Particle in a 1D box. You did not solve? They did not give you even the equation. So what did you learn from quantum mechanics then? You are all from Salem or Namakkal something you said? Salem, Namakkal. Huh. See, this will be a bad thing for the entire district. Chennai people will start saying that, okay, Salem people doesn't know even particle in a 1D box.
It doesn't fix them as a Salem people, sir. They are all in one.
Okay, madam, I am not trying to create this one, okay? What I am trying to ask you?
Why do you compute it?
Answer. Answer from that side. Those who... When energy is important? Where all you have studied energy? Everywhere means, see, when you are saying that I have studied energy everywhere, then you have to give the answer quickly. Break down something to form a bond. Then to rotate a molecule. How many of you studied thermodynamics? Studied? Okay, thank you. Now Tamil Nadu is united suddenly. Huh? So what are the things? Energy came. Come on, yeah, simple questions. Mass into velocity. What is mass into velocity? Is it energy? How many of you studied Gibbs free energy? Internal energy? Enthalpy? All of you studied, but none of you replied. So all of these things are what? Energy, right? So any system that you consider, you will be interested in identifying thermodynamically. For example, if you are interested in calculating the thermodynamic properties, what you wanted to see first thing is energy. Whenever you are seeing whether a reaction is spontaneous or not, what kind of energy you will be computing? Gibbs free energy. If the Gibbs free energy is negative, then spontaneous reaction. All of these things you have studied, but whenever I am asking a question, it is not coming because you did not ask the questions when you are studying. I am repeating this point again. You are studying just because someone else is teaching. You are not studying because you have a question. It is not your interest in learning any of these concepts. That's why these are not going inside your head. You have to frame the story. You have to ask the question, what is this particular subject? Why this subject is useful? As long as you are just learning when the teacher is teaching something, you will never understand. In olden days, how it used to be, the Shishya has to go to the Guru and ask the question, then only, not immediately Guru is used to tell, they have to serve, they have to do this one, that one, and then finally, when this guy is very nice and happy, then they used to teach. So Shishya is very ready, whenever they are telling, immediately to take. Now freely the knowledge is given, the Shishya doesn't have the question. That's the problem. I'm not trying to highlight that model. What I'm asking is, like those people, you should have questions first. Why we are studying this? If you ask the question, many things will become clear to you. Who is getting advantage by that? You people only. If you are not asking the questions just like that, tell me whatever you will tell, I will listen. This is not good. Okay. So why are we computing energy? If I wanted to identify whether a drug molecule will go and bind the protein, I have to calculate binding energy. I am throwing an atom or some molecule onto a surface, then I have to calculate adsorption energy, whether that adsorption energy works or not. So like this, if you consider any particular thing, whether it is in thermodynamics, whether it is in biology, whether it is engineering, whether it is in science, all disciplines will have a need for computing the energy or identifying the energy. So that's what we are doing. So how do we compute energy classically? If I consider total energy of a system as something, how do you divide the energy into? Kinetic energy and potential energy. How do you calculate kinetic energy classically? What is the formula? Half mv square or p square over 2m, where p is the momentum. Okay. In order to consider the complete the total energy, you need to know the kinetic energy as well as the potential energy. How do you compute the potential energy? mgh. That is what kind of potential energy? At rest. Yeah, potential energy means it's the energy at rest. But what kind of potential energy is that? Now we will see the words coming from the mouths. Come on. What kind of potential energy is this? This potential energy is coming because of gravitation, right? So that this is, if it is like electrical, if it is, has to come electrostatics, then what kind of potential energies you have seen? The gravitational potential energy is nothing but mgh, that is coming because of that g is there, because you have a mass and you have a gravity, that's why at particular height that particular potential energy is there. Okay. Similarly, if I wanted to understand electrostatic potential energy, I have a charge at one particular place, I am trying to move it close to a nucleus or a positive charge. What is the electrostatic interaction, or what is the electrostatic potential energy? How do I compute that? How do I compute? What is the formula? You guys told a formula for V equals to mgh for the gravitational potential energy. I am asking a similar question for what is that for the electrostatic potential energy. Physics gone. +1 +2 physics. Okay, Coulomb's law. Tell. M1 M2. Okay. Q1 Q2 by, and anything else is there? What is on the left hand side? Q1 Q2 by R square. Let us assume that it is on the right side. What is there on the left side? Force. 1 by 4 pi epsilon naught Q by Q1 Q2 by R square is the force. From there, can you calculate the potential energy? Do you remember potential? Formula for electric field? Those are all the same, right? It will be very close to each other. Energy. F equals to, how F and E are related, potential energy and the force are related. Any idea? What is the gradient of potential energy? Negative gradient of the potential energy is nothing but the force. Okay. Okay. Since this is going like a formula, I don't want to teach you like a formula. You go back and read it. So you can see that if you have two particular surfaces, you can see the work done to move from one potential energy surface to the another potential energy surface. Similarly, work can be considered as F dot ds. This much you have studied, right? Force into displacement can be seen as the work. So from these two, you can derive that F equals to minus grad U. Okay. You go back and check that. How gradient of potential energy is equal to the force. You check that. So therefore, minus 1 by 4 pi epsilon naught Q1 Q2 by R is nothing but the potential energy. Okay. Between two species having Q1 and Q2 charges. Is this clear, everybody? So potential energy, whenever we are saying classically, classically there will be multiple ways of potential energy. So when it is at rest, whether What is its energy with respect to, because of the gravity acting on it. This is a force that is acting. Depending on the forces that are acting, there will be having the corresponding energies. Since force coming from the gravitational force is acting, there is a gravitational potential energy. Similarly, if you have electrostatic force corresponding to that, there will be electrostatic potential energy, and so on and so forth. Okay. So this is how you will be considering the total energy. Any other quantity, if I wanted to compute classically, what should I do? What is required for me? If I wanted to calculate force, what is required for me classically? F equals to ma. Very good. Ma, A means, how do I get it? What is the formula? Velocity by temperature, time, dv by dt, not velocity by time, dv by change of velocity. And how do I get velocity? ds by dt or dx by dt. So if you know the change in the position, you will be able to get the velocity, and if you know the velocity, you will get the force. So this means what is required for you, or in other words, position. Okay, this is one is required. So can you tell me what else is required? If I wanted to calculate angular momentum of the particle, just now one of you told the formula, L equals to dash cross dash. Like that only I have to ask, otherwise the formula will not be in memory. R bar cross P bar. Okay, so R is what? Position. P is momentum. Okay, so in general what you need is positions and momenta of the particles. If you know, you can calculate any property that you want. Okay, F equals to dp by dt. Have you studied that? Rate of change of momentum. Okay, that can also give you the force. Also, as you have seen, m dx, d square x by dt square also will give you the force. Similarly, any other property, torque, if you want, torque is nothing but R bar cross F bar. F itself can be written as dp by dt. So like this, in classical mechanics, if you wanted to understand any specific property, what you need? You need the positions and momenta. Okay, so this is also called as phase space. What is it called? Phase space. This also you can find so many YouTube videos. Please go back and explore what is phase space. So essentially, if you study any classical mechanics book, like for example Goldstein, is there a book called by Goldstein? Try to see. Again, all of these things will not be very easy for you to, just like a novel or something, you cannot read. Only if you have questions, immediately you will see that the answers are written in a nice manner in that particular books. If you don't have questions, they will look like equations and it will be very difficult for you to understand. But the moment you have a question and you go back and read, you will see how beautifully these books were written. Okay, so all these books which became very famous, no, all of them are famous only for those people who read them with some questions. Okay, I am reiterating that if you ask the question, if you read these books, you will find them very attractive. Okay, next, so you have to, if you wanted to calculate any specific property classically, what you need to do? You need to have the positions and velocities or momenta. Okay, if you have this, you can calculate any property. As I have told, if I need to calculate torque, angular momentum, any particular rotational kinetic energy. Rotational kinetic energy means kinetic energy rotationally, L square by 2I. I is moment of inertia. Only formulas we remember, right? Moment of inertia, what is that? Okay, I don't want to go, time is going up. So like this, we will be able to calculate any particular property you need. All you need is positions and momenta. So what do you need to compute quantum mechanically? In classical mechanics, if I tell the positions and velocities of the particles, I can tell. So one more example here. For example, if you remember projectile motion, you might have studied. So if I wanted to know the position of the particular ball that I am trying to throw after some time, what I need? All I need is, I need the initial velocity, I need the force with which I am actually throwing, or velocity with which I am throwing. Then using the Newton's equations of motion, I can easily calculate what will be the precise position of the particle after some time, the ball or whatever that I am throwing, right? So classical mechanics is very much deterministic. That means if I know something at this particular moment, I will definitely know what will happen to that particular particle at a later stage. For that, all I need is again positions and velocities. That's all I need. If I know them, I will be able to tell. Of course, forces are required and time taken. These are the normal things, mass of the object, etc. But major thing is positions and velocities for classical motion. And classical motion is always deterministic. Deterministic means if you tell me what is the initial time, initial position, I will be able to tell definitely what is the final position, final, all the other properties. Okay. Quantum mechanics is not like that. Quantum mechanics is probabilistic. You might have studied this part also. You have learned probability only because quantum mechanics is probabilistic. Okay. At this junction, can you all stand up for 1 minute? I just asked you to stand up, not because I wanted to sit down, but just to make sure that you are awake. That's all. Okay, so what we are discussing now? Probabilistic. So quantum mechanics is always probabilistic. For example, if I wanted to tell where the electron is, I cannot precisely say this is the position of the electron. This is what you learned through the uncertainty principle. You will always have delta x, delta p. This is what you will be saying, because if you are trying to precisely position a particular thing, you will not be able to completely describe. So either you can tell precisely is the position or the momentum, not both of them simultaneously. This is what we have learned through the Heisenberg uncertainty principle. And as I told you earlier, if it is classical mechanics, I need to know precise. If I know precisely the position and momentum of the particle, I can tell what it and how it behaves in the future. But quantum mechanics is telling what? In the first place, you cannot tell me precisely what is the position and velocity. Therefore, I cannot tell anything about any system precisely in the future, not in the present also. So therefore, it is all about probability. I can tell that most likely this electron will be there with that carbon atom, that edge carbon atom or alpha carbon atom. I can tell most likely. I can never say that 100% this electron belongs to that particular carbon atom. Okay, so that is the probabilistic nature. But the question that I have posed there, what do you need to note in order to compute any quantity quantum mechanically based on whatever you have studied? In classical mechanics, it is the positions and velocities. What you need in order to compute quantum mechanically? Think from the time independent Schrodinger equation, what is required for you to calculate energy, for example? Velocity. So all you need, you can sit down now, all you need is wave function. Wave function itself will have the dependency on the positions and time depending on whether you are dealing with time dependent Schrodinger equation or time independent Schrodinger equation. Okay, what you need is wave function. If you know the wave function, you can compute the corresponding quantity. What else is required apart from wave function? You might have studied, at least the teacher might have told you that in quantum mechanics, if you know the wave function, you can compute any property of the system. This much your teachers taught you? Yes? So this is the reason. Okay? So there, as I said, in the phase space depends on x comma p, whereas quantum mechanics is telling that if you know psi, you know everything about the any system. So if you wanted to know about the entire universe also, you have to write the wave function for the universe. If you want to know about the electron, you have to write the wave function for that particular electron. Apart from constructing the wave function, what you need is also the operators. Okay, so in quantum mechanics, apart from wave function, if you wanted to calculate a specific property, you need to have the corresponding operator. Okay, If it is energy, if you wanted to know the energy of a system, you will be required to know the corresponding operator, which is the energy operator, also known as the Hamiltonian operator. Fine. This Hamiltonian term is coming again from classical mechanics. If you would have known classical mechanics, you would not be worried why they are calling it Hamiltonian. Okay. So earlier classical mechanics, there are various ways to consider the dynamics. In one particular approach is this Hamiltonian dynamics is there. Another one is Langevin dynamics is there, etc., etc. So anyway, so this is the Hamiltonian is nothing but the energy operator for us, and this energy operator consists of what? Energy is divided classically in what ways? Just now you told, you divided it into two, kinetic energy and potential energy. Same thing you have to do here, even in the quantum mechanics. So in order to calculate, you can switch on the lights if you want, for these two only. In order to calculate any specific property, all of you should see here, he will do his job, you should do your job. So this is your psi wave function. In order to calculate any specific property, if I have an observable, observable is generally represented with O, don't consider it as 0. So if you consider any specific observable, for simplicity I am writing it as A. If I need to calculate this, what is the protocol that was given to you? You need to calculate what is known as the expectation value. Have you studied this? No? Yes? Yes and no. Okay. So in order to calculate this, you have to have the operator sandwiched between the wave function, and if this wave function is not normalized, you have to further normalize the wave function in order to finally obtain the property. Okay. So this is called as expectation value. Expectation value means essentially average value. As we said earlier, quantum mechanics is not deterministic, it is probabilistic. So all you can tell about is average values. Probabilities only you can tell. You cannot tell anything deterministically. So in order to calculate any particular property, if it is energy, if this is the energy of the system I wanted to calculate, the corresponding operator, if this is E, the corresponding E operator I have to use. If it is P, the corresponding P operator I have to use. P is momentum if I am representing. Similarly, if I need to calculate L, the corresponding L operator I have to use. This is what you have to do. This is the protocol. So now, in order to calculate energy, Hamiltonian, energy operator is always written as Hamiltonian, just to remember that person. So this is nothing but the kinetic energy and the potential energy. Kinetic energy in classical mechanics, you know that this is nothing but P square over 2m. And potential energy is depending on what kind of potential energy that you are using. Considering the gravitational potential energy, this is written as mgh, I am writing as x. I can write whatever I want there, okay. So this is what we are dealing with. Now, if we are seeing what you should do in quantum mechanics is, wherever P is there, you put a P hat, wherever x is there, I already kept, that is x hat. That's all you have to do, okay. That you are converting the Hamiltonian into an operator now. This hat corresponds to an operator. Operator means you can represent like a matrix, okay. So this is your system. Now what is the P hat means? What is the P operator? If you have studied quantum mechanics a little bit, again I don't want to derive that complete equation, but P hat is nothing but minus IH cross dou by dou x, only for Px along the x direction this is, right. So now if you use this, and if I wanted to understand Px square over 2m, what it will become? Minus h cut square by 2m dou square by dou x square. So similarly I can write Py square by 2m, Pz square by 2m. Then what will happen? Dou y square, etc. So what does that mean? Wow. That is 3 dimensions, agreed. So then what will be the T operator belongs to? How the T operator would look like? T operator would look like minus h cut square by 2m if it is in 3 dimensions, and if you are writing in Cartesian coordinates as x, y and z, you would be writing it as dou square by dou x square dou square by dou y square plus dou square by dou z square. That's all. This is your t operator. And the x operator, how do you write? X is nothing but simply x only. That means position is position. I don't know Tamil, sorry. Term is I square equals to minus square is so you have to square the minus also, brother. Understood or not understood? This minus square became plus, this I square became minus. That's why it is minus. Fine, no problem. Okay, at least he is attentive. Can you clap for him? Thank you. Okay, now go back. So this is your Hamiltonian kinetic energy part. Potential energy part, x is simply x. So now you considering this is for one electron along in the 3 dimensions. If the electron is moving in all the 3 dimensions, and if it is in the gravitational potential energy, this is how I will be writing the Hamiltonian. For those people who have all, what sir? You take full and square, madam.
Sir, we consider minus 1 as whole square means we get plus 1 only, no sir. Like that we will square minus 1 whole square means we get plus 1.
Minus I, can you take and square it and tell me what it is happening?
I square
Minus I
minus I
whole square.
whole square. I square value is minus 1 only, no sir.
Minus I whole square. What is the value? Answer I am asking. You are not kid, no? You should tell me what is the answer for that. You don't understand means you have to do. Wait, please let her do. Minus I into minus 1 into minus 1, can you do? Please, all of you stop, let her do. Minus 1 into minus 1, what is the answer? What is the answer?
I am getting minus 1 only.
Minus 1 into minus 1 is minus 1 you are getting.
Plus 1.
Plus 1 you are getting. Now replace the 1 with I
Then we will get plus I.
square. Yes or no?
Yes sir. I square value minus 1 so that.
Minus 1. Fine? You understood? Very good. Now let's go back to this part. Enough. That is done. That chapter is over. Let's concentrate here. So now you have the Hamiltonian. So what we have written here, kinetic energy, and this is the potential energy, depending on whatever. So if I am considering only along the one direction, if it is in 3 dimensions, I can consider it as like some r, mg, r it will become, where r is the position instead of the x. Okay, all of you are with me till here. So now, if I wanted to write the full Hamiltonian of a system, so if it is one electron, what I need to do, I have to tell this one that electron is there in the 3 dimension, so electron can move in any direction. That kinetic energy operator is like this in the 3 dimensions. If I have one more electron, what I will do, I have to sum them up for each one. Instead of writing x, what you will write, x1, y1, z1 is first electron, x2, y2, z2 is second electron, and so on and so forth. So I will be summing over all the possible electrons. Similarly, if I have nuclei, what I should do, I will be summing over all the nuclei separately. That will be my kinetic energy operator. Potential energy operator, generally when we are dealing with molecules, we do know that gravitational effects on them are very poor because their masses are very negligible. What is the mass of an electron? Very good. 9.1 into 10 to the power of minus 31 kg, right? Minus 31 kg. So how much amount of gravitational force if you put also, it will be minus 30 only, right? 10 to the power of minus 30 is a very, very negligible number. Therefore, we generally, whenever we are dealing with molecules, we will neglect the gravitational effects, but we will consider the quantum effects or the electrostatic effects. So when you are considering these electrostatic effects, electrostatic potential is the one that you need to consider. And earlier we have discussed that electrostatic potential will be described as 1 by 4 pi epsilon naught Q1, Q2 by R, not R square. R square is force. Potential energy is like this, okay? So this is more like V of R. So if Q1 and Q2 corresponds to two charges, I will write here R1 and R2 and I will put the modulo, because if this is the first electron, if the second electron is there here, again please do not think that this is the correct picture, but the picture that we are trying to tell is like this, okay? In reality, electrons will neither be particles nor be waves, okay? They will be having dual behavior. So if it is at R1 position, R2 position, the distance between them is modulus of R1 minus R2, because that is the vector you will draw for R1, this is the vector you will draw to R2, and this vector is nothing but the distance between them, R1 minus R2. So this is what you have written, and Q1, Q2 in this case will be simply E square if both of them are electrons, okay? This will be replaced with E square, okay? If it is actually a nuclei, then what you will write? Z into E, okay? Those many, whatever the atomic number into that many number of electrons, but with positive number, and this is a negative one, okay? So that will become, so if it is a nuclear electron interaction, then it will become minus Z E square divided by capital R minus small r, where capital R corresponding to nuclear position, small r corresponding to the electron position. If I have 10 electrons and 20 nuclei, I have to sum this over each of the nuclei. Let us consider capital I, each of the electron, small I. Okay. If there are 20 nuclei, I will be starting from 1 to 20. This is 10 electrons, 1 to 10. ठीक है? Okay. Okay. Similarly, electron interactions will be I and J, you will put Ri minus Rj, you will put 10 electrons, sum over I equals to 1 to 10, J equals to 1 to 10, you will calculate it. Is this clear? How do you write the Hamiltonian operator? Okay. Nucleus also you will be writing. So in general, when they are writing, they will generally, because several things are there here, several equations are there, they will write it in what are called as atomic units. While they are writing in atomic units, they will have some approximations, not approximations, conventions. They will consider 1 by 4 pi epsilon naught equal to 1, mass of an electron equal to 1. This is just to avoid writing a 9.1 into 10 to the power of minus 31 every time. They will consider like this. They will consider Bohr's radius equals to 1. Okay. They will consider electron charge is equals to 1, like this. So you can convert the units from one to the other, right? You know how to convert from kilocalorie per mole to joules, right? Joule per mole you can do. Like that, they are just converting from atomic units to other units. If you do that, this is how the Hamiltonian of any system would look like. Can you see and understand? Don't need to write this, please. Don't write it. I want you to see and appreciate whether you are understanding each of them or not. First term is what? You know what is this symbol called? Del. What is it called? Laplacian. What is it contains? Right? So further h cut is also considered as 1. So therefore this h cut square over 2me, whatever is there, this is considered as half. So that's why you are seeing this half here. And then del I square, that is nothing but this one, Laplacian. Okay? Summed over all the electronic positions. The next one is summed over all the nuclei. Since me is there, that is 1, but this is the mass of the nuclei, so therefore that m is coming again. Are you able to see the second one? Please see here, second term. Okay. After that, what? These are the kinetic energies. After that, after the kinetic energies, what are left? Potential energy. See, this picture is coming from that first picture that I have shown you. Any particular material can be seen as bunch of nuclei and bunch of electrons interacting with each other through electrostatic interactions. If I have a bunch of nuclei that are moving, bunch of electrons that are moving, their kinetic energies can be written in this manner. Agree or not agree? Agreed. Next one is, what are the kinds of interactions that are possible? If you have a bunch of electrons, bunch of nuclei, what are interactions, electrostatic interactions are feasible? One is electron can be repulsion or attraction. Electron nucleus will be, nucleus will be, that's all I have written, the three others. So this is what? Nucleus electron, you can clearly see that, right? Since E is equals to 1, I have considered this is Zi only, it has there. And the summation is over all both of them, okay? I and small and capital I. Second one is Ri minus Rj. This is what? Electron, because this is a repulsion interaction, there is a positive sign. Attractive interactions are negative sign. Similarly, the other one, internuclear repulsion as well. Okay, so like this you will be constructing the Hamiltonian. So once you construct the Hamiltonian, how do you get the wave function? You will get the wave function by solving actually the time independent Schrodinger equation. If you guys have solved actually particle in a 1D box, you would have known this part. What you will get? So for the particle in a 1D box, only 1D box means only one dimension. The Hamiltonian is simply minus h cut square by 2m d square psi by dx square. This is what is the Hamiltonian, and this is equal to d square psi equal to e psi. This is what you have to solve. This is what a differential equation. In order to solve this differential equation, you can use various methods. Okay, so one of the method is like power series. You might have studied, if you have studied particle in a harmonic oscillator, etc. If you have studied, if not here, you can start assuming the boundary conditions and you can start guessing with the wave functions. You will start guessing with e power x or sin x or cos x, like that you will see, and you will find the solution for this. What is the solution for the particle in a 1D box? Those you studied, psi equals to square root of 2 over L sin n pi. Okay, that means you guys did not study most likely the particle in a 1D box, that's why you are not able to see. So this is like the simplest equation. Particle in a 1D box means a particle is there in a one dimensional box where the potential energy is 0. If the potential energy is 0, what is left there? Kinetic energy. How do you write the Hamiltonian? Kinetic energy. What is the kinetic energy? Earlier only we told, only one dimensional, minus h cut square by 2m dou square by dou x square. That's all is there for you, and that psi equals h psi. H is a minus h cut square by 2m d square by dx square. This is your h, and this is psi equal to e psi. What you are trying to solve? You wanted to know the wave function, you wanted to get the energy for this particle which is there in this one dimensional box where the energy V equals to 0. Here V equals to infinity. This is what they will start and show you. Okay, so to solve this, you will first start with any differential equation. When you are solving, you need to have the boundary conditions. If you have studied mathematics differential equations, they will always give you the boundary conditions in order to solve this. The boundary conditions for this is, those are called limits. Those are not boundary conditions. Those are called limits. So here what's happening, the wave function cannot have infinite amount of energy. If a particle is there here, what does that mean? V equals to infinity means it is staying in a place where V is equal to infinity, right? If V is equals to h means what? The particle is there at the position h. Similarly, V equals to infinity means the particle is staying at V equals to infinity, which means what? It has potential energy how much? Infinite potential energy. Can any particle can have infinite potential energy? No. If since any particle cannot have infinite potential energy, therefore particle should not be here. Particle should not be here means what should happen? The wave function could go to 0. Psi must be 0 below this particular place. Similarly, psi should be 0 after this place. If you are calling this as the 0 and this as the L, L is the length of the box, then psi must be 0 at less than 0 or greater than or L. This is what. So if you solve this one, you will see that psi will be having some ground state, psi will look like that. Okay, I am not going to solve the particle in a 1D box right now, but this is very simple there to solve. Psi, you can see that kind of a differential equation will have e power ikx is one solution, sin kx is another solution, cos kx is another solution, like that. So if you solve that, psi, finally you will be obtaining the result. Psi is equals to square root of 2 over L sin n pi x by L. This is the wave function. The possible wave functions that you are going to get are these. Similarly, if you are solving energy, this will be n square h square by 8m L square. This is again the answer that you will be getting by solving that one. Okay, this is for En, where n is the quantum number. Again, as we know, these are the separate levels you will be getting. Not everything will be obtained. So we need to discuss a lot more. I have kept a lot of slides, but the time is very quickly over. So So this is for the particle in a 1D box. This is all it is about. I mean, I did not teach you actually particle in a 1D box. I just showed the solutions. So in order to obtain the energy, what you did is you solved the time independent Schrodinger equation. So that is a differential equation. Solving differential equations will be various ways. One way is power series methods. Okay. So that's what you will be learning if you did not learn yet for solving other kind of one-dimensional systems or single particle systems like hydrogen atom. If you wanted to solve, you need to use the power series method. Harmonic oscillator problem, that means the particle is there in a harmonic potential well. Have you seen this problem in your book, textbook at least? That particular problem also you can solve using power series method. That's where you will be learning about what are called as Hermite polynomials. Okay. Similarly, when you are solving this hydrogen atom problem, you will be learning about Laguerre polynomials. Okay. So there is another one, angular momentum problem. If you are solving, you will be learning about Legendre polynomials, etc. So these are mathematical parts that you are learning essentially to solve the differential equation. Your aim is to solve this differential equation in order to obtain the energy. Are you following me? In order to get the energy or any other property of a system, I need to get the wave function and the corresponding operator, as we have discussed earlier. In order to get the wave function, one of the ways is to solve the time independent Schrodinger equation. In order to solve the time independent Schrodinger equation, you have to solve a differential equation. These differential equations will have numerical possibilities, but if you want to solve it analytically means using a pen and paper, if you wanted to derive a formula, that is only feasible for one electron systems. The moment you have two electrons in the system, you cannot solve it analytically. That means you cannot solve using pen and paper. Therefore, you need to go to computers. So the problems that everyone is interested in is not one electron systems. What are one electron systems? Hydrogen atom. What is the other one electron system that you know? Huh? Deuterium. Good. Deuterium. That's all. Helium plus, lithium 2 plus, beryllium 3 plus, all of these will be one electron systems only, but you will not be too much interested in any one of them unless in special cases. What you will be generally interested? You might be interested in benzene molecule or a styrene or something or something or something. The clothes that you are wearing, etc. These are polymers. You wanted to consider them, etc. So that means you will be interested in bigger molecules, not like in one electron systems. The moment you need to go through the bigger systems, you need to have a completely different machinery. Okay. So that machinery corresponds to these electronic structure methods. If you heard of Hartree-Fock theory or density functional theory, all of these things are enabling you to study these multi-electron systems. Anything beyond hydrogen atom is a multi-electron system. For example, helium atom is a multi-electron system. In order to study this, you need to employ new things. Like, although I did not teach you anything of how to solve the differential equations. For example, I did not teach you Hermite polynomials, power series methods. I did not teach you. But this is something that you need to go back and see how they are solving for one electron systems. If you know and understand how they are solving the one electron systems, then naturally a question will come to you how to solve the two electron or multi-electron systems. Still one electron systems, things are simple. The moment multi-electron systems comes, that's when the Pauli exclusion principle that you might have studied in +1, +2 will come back. Okay. So the wave function has to satisfy this Pauli exclusion principle. So this stepwise learning is required. I cannot give all the content right now in the next 7-10 minutes. But essentially you will always be solving the time independent Schrodinger equation to obtain the psi. The moment you obtain the psi, in general when you are solving time independent Schrodinger equation, apart from psi, you will also be able to get the energy as an extra bonus you are going to get. But for any other property, you have to again apply that operator onto this particular wave function in order to get that final value, like that expectation value that I have shown you earlier, that you have to do. So these are some of the things that you will be studying: particle in a 1D box, harmonic oscillator, hydrogen atom, etc. These are all one electron systems. The moment you have to go to the multiple electron systems, you have to employ various kinds of approximations, including the Born-Oppenheimer approximation, and you will be going through the variational principle. So essentially what is Born-Oppenheimer approximation is, you are saying that since the electron's mass versus the nuclear mass is so heavy, okay, when the electrons are moving, nuclei are simply adjusting, not that much quickly, very slowly. So within the electron's perspective, the nuclei is always more or less static. In other words, I can separate the nuclear degrees of freedom from the electronic degrees of freedom. That means electrons' influence on the nuclei is very limited, is what we are considering. Okay. Again, as I said, in reality, electron will have an influence on the nuclei, specifically when they are in some kind of, they call it conical intersections, etc. Essentially, whenever there is a strong force of electron acting on the nuclei and nuclear motion is affected by the electrons, it is the non-adiabatic dynamics which I said earlier. So this Born-Oppenheimer approximation will fail. For example, when you are detonating something, some blasts are happening, then Born-Oppenheimer approximation doesn't valid. When light is shine on the system, then this Born-Oppenheimer approximation generally will not be valid. So the Born-Oppenheimer approximation is this much: nuclei are heavier than that of the electrons. Therefore, you can neglect whatever is there in the nuclear kinetic energy, because nuclear kinetic energy will become naturally 0 when you are assuming that nuclei are static. Nuclear kinetic energy will be 0, and nuclear repulsion is just a constant. Since nuclear static, you can easily calculate using the Coulomb's law what is the interaction between them. That will be just a constant, so you will neglect that as well, and you will come to this particular psi electron, this particular 3 terms only in the Hamiltonian. This is what is called as the electronic Hamiltonian, and this is generally what you will be solving on a computer. How much you are following? Following? Okay. So this is what we will generally solve on a computer within the Born-Oppenheimer approximation. So using this, next things are there, but now I am skipping so many slides and directly going to the problem. I will tell in maybe 5-10 minutes only, whatever we have studied for the anode problem. So like this you have to study in order to calculate the energies. Okay. So these are the variational principle, how the spatial orbitals, etc. are there. I thought I will be able to easily cover all of that, but I could not. This is how generally a simple system you will start, and you will be, for a water molecule for example, you will have a computational software package. Without knowing whatever I taught you, you can simply submit like this and you will get the energy and the wave function. This is how many people are doing here already. Okay. I am not interested you to do like that. You should know and then do. But the current situation is that you can simply do all of these calculations without even knowing the entire details. This is like a black box. Just throw it, it will give you something, you take it and use it. That's all. These are scaling, but we will not. Okay. Any questions still here before going to the next part? Any others? Any questions? We have started this class 12 minutes late. That's why I'm asking still. Any questions? No. Okay. So how do you compute the electrochemical properties is the point I'll try to cover in 5 to 7 minutes maximum, so that you will have 5 minutes more for break. So what we have here is anode materials. What I wanted to know is whether this material is useful or not. So now if you pay attention, we will do it very quickly. So first question that you should ask is, why are we studying the energy storage devices? Why? To store energy. Applications are more. Why are we interested? Because we wanted to move towards the renewable energy storage devices. All of you might remember this guy, Ukraine war. Now already Iran-Israel war is also started a few days before. So Israel is bombing Iran everywhere, and several oil sites are already gone. That means our oil prices will increase. There will be protests outside on the roads for us, but nothing will help because we are still dependent on the oil for our energy needs. The population is increasing, not only for India, everywhere, but India it is much more important. We are #1 population. We have large amount of energy is required, and all this energy is coming from non-renewable energy resources, specifically oil. If you are dependent like this, if there is a war, who is suffering? If Israel has a problem with Iran, we are having a problem in our home. Are you understanding this? So that this geopolitical situations are affecting us very largely. That means what we should do, we are becoming very dependent on outside people. Do you want it to be like that? No, none of us are interested in becoming like that. Therefore, you wanted to change to renewable energy resources. What is the issue with the renewable energy resources? Issue is these are intermittent. That means if I wanted to, this is all there. So if you consider any of these kind of resources like solar energy, the moment right now I am not feeling very cold, so I will go and switch on the fan. Immediately the fan will rotate and gives me some air. I will switch on the AC, it will give me some cool breeze. This is happening because someone else is sending the electricity continuously to your home. But if I wanted to get this energy using solar energy, for example, I will ask sun come. Will the sun will come? No. If I ask the wind to blow, will the wind will blow? No. If I wanted to create a dam here, can I create? No. So these kind of energies, the renewable energy resources like solar and wind energies, they are time and weather dependent. Similarly, geothermal and hydropower processes are location dependent. So these are like not continuously energy cannot be provided. But if I have oil, I can continuously burn. That's what they are doing. They are burning coal or something. That's how you are getting the energy, right? So these energies are intermittent. When the energies is not continuous, when it is intermittent, what you need to do? If you wanted to use it continuously, you have to store it. That's why we are storing the energy. Okay, that's why we are using the energy storage devices. So here, whenever we are saying here, please understand that if the whatever the Tamil Nadu government is not providing you the electricity continuously, okay, what will happen? They will first cut off that, but they will give only to industries or something. If they are doing regularly, how do you feel? Very bad, that you don't want this kind of government. You want continuous electricity, because when you are watching a movie, you don't want it to be interrupted 5-6 times, right? So this is the reason we are trying to store the energy. Okay, if you are generating the energy using these kind of renewable energy resources, you have to first of all store. Among various kinds of storage places, lithium ion batteries are cheaper, okay, and portable. It's not only about cheap. I can store it in a different way and it is cheap, but this is portable. You have your mobile phone, everyone is carrying it. That means you can take it anywhere that you want. That's the reason lithium ion batteries technology and that one has become more and more and more. And this has captured the global market, etc. I am not going into those details. Do you all remember the principle of the rechargeable battery? Yes? If yes, I will skip and go further. Yes, okay. So essentially what is happening during the charging, some metal atoms are moving from to the cathode to the anode, these are it is lithium, and during the discharge, these ones are coming back. I will ask the question, why this is charging, why this is discharging? I asked. Answer I am expecting. So this is the thermodynamically stable state. Okay, wherever the cathode it is there, that is a thermodynamically stable state. That's why you have to give some bias to push them towards the anode. And when you left it, discharge time, because this is the thermodynamical stable state, it is just falling back to this place. It is like pumping the water uphill, and then if you just open the tap from uphill, it will simply come down. That's what is happening here. Okay, so like this, among the different kinds of things, like again as I said, lithium is one thing, but if I wanted to consider the energy batteries, if I wanted to use for electric vehicles, the current energy densities are not sufficient. Therefore I have to go to alternative battery technologies. So the issue with the lithium ion batteries etc are the raw materials that are there with the lithium. Raw materials for the lithium ion batteries are very scarce. All of you might know this. For example, cobalt. What is the lithium ion battery has? Cathode material as lithium cobalt oxides. Cobalt is there only in the Congo, African country. Okay, we don't have it. So why do you want to go back from non-renewable energy resources to renewable energy resources? We earlier discussed a few minutes before that we don't want to go with the renewable energy, non-renewable energy resources. I wanted to go to the renewable energy resources. For what reason? Because geopolitical tensions will have an effect. We don't want to be dependent. We wanted to be independent. That's the reason we are going to the renewable energy resources. But now if I wanted to use lithium ion batteries, I have to go back and ask someone for the cobalt. Am I dependent or independent? Dependent. So So therefore, again, you need to consider materials that are alternatives to lithium ion batteries. It is in this context we need to search for alternate anode materials and cathode materials, etc. Among them, we have tried recently with one of the material which is called as the cobalt antimagazines, etc. The material, it doesn't matter, whatever the material you have to search. So to identify, this is the last slide I will show, there are various things. How do you identify a material is good or bad? It has to be thermally stable, it should be dynamically stable, it should be mechanically stable. Similarly, the metal atom should come and adsorb on this, right? Like when you see this principle, from the cathode, the metal atom is coming and sitting on the anode. So it has to come and adsorb. It should not adsorb very strongly. If it is adsorbing strongly during the discharge time, it will not come back. So therefore, it should have a moderate affinity towards the metal atom. After that, the anodic voltage should be lower. Why the anodic voltage should be lower? Total cell voltage is given as cathode minus anode. If total should be more, anode if it is less, cathode minus anode will become big. If voltage is of the cell is more, then the energy density can be more. If the energy density is more, I can use it in electric vehicles and various other things. Migration energy barrier. So when you are moving, not only one atom will move, multiple atoms will suddenly come back into the electrolyte and then go towards the cathode. So migration energy for all of them, it has to jump from one place to the other on the anode surface, that should be low. Finally, when you are moving, removing, etc., if the structure is distorted, then that will be dangerous for us because it can bulge. If your mobile phone starts to bulge like this, will you be trying to keep it in your pocket? No. Why? You are scared of explosion, right? So those are the things that we will be studying. Again, for each one of these things, there are ways to study using computers. Unfortunately, I am unable to show you now, but I will just flash the slides. These are the materials. This is how we will start with the system. We will calculate its first property called dynamical stability. If you see the phonon spectra, if there is no negative frequencies, we will call it as dynamically stable. I thought I will explain you this entire process also. After that, we will try to see the electronic structure, whether it is a conductor or not. For that, you will be doing what is called as band structure calculations. You might remember the band theory. If it is a conductor at the Fermi level, there will be bands. If it is a non-conductor or a non-metallic system, there will be gap. All of these systems do not have any gaps, so therefore these are metallic systems. Then we calculate the adsorption energies, for which you need the energy calculations as we discussed earlier. So we will calculate using the time independent Schrodinger equation and you will obtain this. And then you will explain why which site is stable, etc. And then you can calculate this migration energy paths from one side to the other. Again, you need to calculate the energies. Similarly, you can calculate the voltages. These kind of equations you might have seen for the redox reactions. We will do those things and we will calculate the voltage. We can explain why this voltage is like this, and then we can calculate what is called as the specific capacity. Once you know the voltage and the specific capacity, you can calculate the energy density. And we found that again, thermal stability, you can run the time dependent Schrodinger equation and you can study the thermal stability of the systems. And then we will be able to finally calculate the structural distortion as well. So this is how we will be calculating all the different properties, and then we can identify whether the system is good or bad, etc. Okay. So this is the procedure. Again, I wanted to show you entirely, but lack of time, we will not be showing. So if you have any other questions, please feel free to write to me, as I have given there, Yamijala group or yamijala@iitm.ac.in. So I have finished 5 minutes before your started time. Okay. They have given me 2 hours. So we started at 9:12. We have stopped 5 minutes before. Thank you.
SwayamPrabha. Digital India. Educated India.